Hello and welcome back to part 2 of this lecture. So we start off from where we ended, but now with a graphical representation for your benefit. Now if you look at the slide here, you see that we were talking about the transformation of area elements under deformation, right. So by under deformation I mean under the deformation gradient f. So since deformation gradient is a tangent space object, we always talk of infinitesimal area elements. Please remember this, because without working with infinitesimal structures on the tangent space, you really cannot derive partial differential equations, right. So therefore this is the important thing, that if you have an infinitesimal area element in the undeformed configuration, which is here. This is my undeformed configuration, right. It is shown here with capital N denoting the normal, right. Then under the deformation you have this area element which is shown here in the undeformed configuration. This area element gets transformed here to a new area element which is shown again here with the modified, which is represented by this new normal small n. So that new normal small n is not just, has not just changed its magnitude vis-a-vis this capital N, but it has changed its orientation also, right. So these n's, neither capital N nor small n need to be unit, okay. So you may start with capital N as unit if you want, but it need not be. Then small n will have a different magnitude and a different orientation. So the Nansen's formula is captured here, right. So and this part is nothing but f c, which is the cofactor of the deformation gradient f, right. Now we come to the issue of principal stretches, because you see this is about the eigen analysis of the stretch tensor U. We said that U is the right stretch, right. It came as part of the polar decomposition of the matrix F, of the tensor F of the deformation gradient. So it is the stretch. Now if you do an eigen analysis of this, right, eigenvalue analysis of capital U, you will be getting the eigenvalues. This is a 3 by 3 matrix for any x and t. So therefore U is a function of x and t always, no. So yeah, so you will be getting the eigenvalues lambda I and eigenvectors Ri, right. And then we can have a spectral decomposition of this matrix U at a given x and t in terms of these eigenvalues and eigenvectors, which is indicated here, the spectral decomposition, which is the sum of the eigenvalues lambda I multiplying with the eigenvector Ri tensor product with Ri. So you may be knowing about tensor product. We talk of tensor product of two vectors like this. If A is one vector and B is another vector, then tensor product of A and B is defined with respect to a third vector, which call it by C, right. This is C, as vector C. This is defined as B dot C, which is a scalar, times A, right. A is a vector. So this is how the definition of, just to recall, this is the definition of a tensor product, right. So basically any tensor product A cross B, a tensor product B of two vectors gives a matrix, right. So Ri, tensor product Ri gives another matrix that is multiplied by lambda I. Sum over all such things will reconstruct U. That is the idea of spectral decomposition. Now instead of eigenvalues, we typically call lambda i's as principal stretches. They are essentially eigenvalues of U, and Ri the principal stretch directions, all right. So the lambda i's capture the stretch magnitudes and Ri's the direction. Similarly, we can do for the left also, but I am not showing all this. And we also can easily see that Ru, F equal to Ru equal to VR. From here you can clearly see that V can be written as, you know, Ru, R inverse is equal to R transposed. So, R transpose, this is exactly what is written here. So, V, the left stretch, is related to the right stretch using this relationship, but we won't be using left stretch much. We use right stretch because that is a material description. So, writing everything in the undeformed description has an advantage because that does not move. Undeformed configuration does not move in space or time. So, therefore, you know, it is numerically more suited for solid mechanics where there is no direct flow like a fluid, you know, to work with the undeformed coordinate cover. So, similarly we can actually, you know, there is one thing that you must understand. So, C was defined as F transpose F. So, this is nothing but U transpose R transpose RU, right, but R transpose R is basically identity. So, F C equal to U square, we already saw that. Now, since U can be written in this decomposition, C can be written, see, for example, U is a symmetric matrix. So, if U is a symmetric matrix, what are the eigenvalues of its square? It is also a symmetric matrix. Square of a symmetric matrix is also a symmetric matrix, but its eigenvalues are also squared, right. All symmetric matrices have real eigenvalues, you know that, right. So, C has the same eigenvectors as its square root U, same eigenvectors Ri, but its eigenvalues are squared. So, therefore, the spectral decomposition for C is simply sum over all I lambda I square tensor product of Ri with itself. Now, we come to the issue of material velocity field. Towards this, we actually should recall what we discussed about the material derivative, material time derivative in lecture 1. We said that the material time derivative of any function defined in the referential configuration is just, you know, take the partial derivative with respect to small t, all right. Now, instead of any function, let us consider the function phi, which is the deformation map itself, right. So, if you take the partial derivative of the deformation map written in terms of the coordinate cover capital X of the undeformed configuration, then you get what is called the velocity, right. So, velocity is nothing, so because phi is nothing but small x, right. So, velocity is nothing but, you know, del xt by del t, x dot, small x dot, all right, you please understand that. But then in many applications, in many of the future work that we will be doing, we will be more interested in expressing this velocity v in terms of small x. So, velocity field that way we should actually write as a spatial vector, right, not in terms of a material vector. So, in the spatial form, because phi is now 1 to 1 and therefore it is invertible, we already know that. So, we can, you know, write v in terms of small x by relating this capital X in terms of small x through phi inverse. As you see that phi inverse of capital X, small x comma t at any t is nothing but capital X, right. So, now with this composition, first apply phi inverse on the deformed coordinate system small x and time t, and then, you know, on that act v, I mean the v acts, right, because v acts on capital X. So, therefore, you know, this composition gives you this v, which is not the same v, this function v and this function v are not the same, because it is a material, this is a material description and this is a spatial description, but then we take them by the same symbol if you understand what we are talking about. Please do not misunderstand. This phi is, this v is essentially a composition of this phi with phi inverse, right, to be mathematically correct. But then I do not want to create two v's, two different velocities, you know, two different symbols for velocities. It will only clutter the discussion and make the understanding a little more difficult later on. So therefore in this latter form, V is in this spatial form, right, and velocity is therefore a very important object. Why is it important? Because it defines strain rates, which are very important instead of strains in plasticity. Because plasticity, under plasticity materials behave almost like, sometimes like fluid. We talk of plastic flow, right, because material undergoes deformation much more easily under loading than it is possible under the elastic regime. Velocity also plays a very important thing in the objective rates, which we have not discussed, that is the frame invariance aspects or frame indifference aspects, and in describing the dissipation as well. We will come to these issues slowly, but for now let us understand the importance of velocity before we discuss them. What is even more important is the gradient of velocity. Just the deformation gradient played a very big role so far. Velocity gradient plays a very important role in plasticity. So velocity as a spatial field is a function of small x. You remember that now. Now take the gradient of velocity with respect to small x, right. We also write it as grad v with a small g to indicate that this gradient with respect to small x but not capital X, small g. Then we get a matrix or a tensor, which we call actually this is called the velocity gradient matrix or matrix field essentially. This is also a function of small x and t, alright. Now any matrix can be decomposed into, any matrix A can be decomposed into a symmetric part and a skew symmetric part. A symmetric, A skew, right, equal to half of A minus A transpose, right. You know this uniquely. You can do the same thing on L also. Call the symmetric part of L, which is half of L plus L transpose, as D, and the unsymmetric skew symmetric part as W. W is also called the spin, right. There is a name for this, spin, and for D there is a name, it is called the rate of deformation tensor, rate of deformation, okay, rate of deformation tensor. Now this is exactly what is indicated here, this how D and W's are expressed in terms of L. And now because L, remember, is related to velocity, it is the gradient of velocity, so it is also a rate. So it is related to the rate of deformation, right. So hence it should be related to F dot, because the deformation gradient the rate of the deformation gradient should have something to do with L. So let us see what is the relationship. So F dot, the rate of deformation gradient, is by definition, you can see this is true, right, del t of grad with respect to capital X of phi. This del t we can take inside, correct, because these are commutable, this gradient operation and this derivative with respect to time, partial derivative with respect to time. So I can call it grad x of v, because del phi by del t is grad x of v, fixing capital X. Now apply chain rule, take this gradient with respect to small x, and then by chain rule I have to take the gradient of small x with respect to capital X, which is capital F, right, which is the deformation gradient. So we get LF, right, because this part is L. So now you see that F dot is equal to LF, or L is equal to, because F is invertible, is F dot F inverse is the relationship between the rate of deformation gradient and the velocity gradient. They are related but they are not identical. Okay, F dot and L are related, but there is an F inverse coming in. Okay. Now what is the structure of L? L actually, if you look at it, L maps a spatial vector, because V is a spatial vector, right. On that I am taking a spatial gradient. So therefore L is a purely spatial tensor, multilinear transformation, and L maps a spatial vector into a spatial vector. So, it is a purely spatial tensor, as I said. Now, some identities are useful. For example, the trace of L, if you take trace of a matrix is the sum of its diagonals, right? You remember that. So, this is the definition of the trace, and trace of the gradient of a vector, it gives a matrix, it is nothing but the divergence of that vector, right, because it is the sum of the diagonals. On the diagonals you have only del v by del x i's, right. So, there are no cross terms there, del vi by del xi. So, right, each gradient, so for example, the first diagonal will be del v1 by del x1, the second diagonal will be del v2 by del x2, and so if you sum it up you get divergence of v, right. So, for any matrix field, now we can use an identity which I am not proving, but it can be easily proved based on the definition of the determinant itself, that if there is a matrix field which is dependent on time, may not be explicitly through its implicit dependence, through the dependence of x on time, for that the total derivative ddt of the determinant of A is given by this, okay, determinant of A times trace of A dot A inverse. Now, instead of A, if I use f here, the deformation gradient here, then what we get is determinant of f is j, right. So, j dot it becomes equal to, this is j again, and this part f dot f inverse, trace of that is nothing but divergence of v from here, you see. So, essentially, because L is, remember that L equal to f dot f inverse, right, that we have used here by replacing A with f. So, what we have got in the process is this expression, j dot equal to j times divergence of v. This is a very useful expression, because in a dynamic case, if you are not solving a static problem, see, all plasticity problems are necessarily dynamic, but unfortunately, but fortunately for many of us, when we do the standard elasticity, we could actually easily solve a static problem also. We can conceive of static elasticity problems under static loading. So, for such incompressible problems, suppose you consider an incompressible elasticity problem. So, j equal to 1 for those cases. But if it is a plasticity problem and if it is nearly an incompressible deformation, which actually is the case for metal plasticity, for much of metal plasticity, then v becomes important, velocity becomes important, and here is another characterization of incompressibility. Suppose divergence of v is 0, then j dot equal to 0, so there is no change in j in time, that means j is fixed right all through the time starting from the beginning at which j was 1, right, because there was no deformation. So, j was 1. So, j remains 1 starting from 1, right. So, divergence of v equal to 0 is a good representation of incompressibility for dynamic problems and hence very useful for plasticity. Let us now consider the physical meaning of d and w, right. So, d, the deformation tensor, the rate of deformation tensor, governs the change of lengths and angles. It governs the change of length of a vector, and also between two vectors it governs so it is a stretching in a generalized sense, but w only governs the local rigid body rotation rate basically. So, you understand that because w represents only the spin, local rigid body rotation, it cannot produce any strain energy, it cannot produce any effect on strain, it cannot produce any change in strain rate, correct. And so, in future we will be requiring frame indifference. That means, so we have to understand what is the character of d vis-a-vis w. That means, if I change the coordinate system of instead of this coordinate system, right, x1, x2, x3, if I rotate it, rotate the whole thing by some q as a function of time, not space, right, rigid body rotation, then there will be a new coordinate system. So, under that if I write d and under that if I write w, then what will happen to them, right. So, here the frame indifference, the notion of frame indifference or objectivity becomes very important. So, let us now talk about it. Before that, so this is a pictorial representation of what W does. It undergoes, it only connotes pure rotation, rate. Always these are rates. So, you should think of these as per unit time, what is happening, right. So, you talk of pure rotation per unit time, it becomes a rate, right. So, I mean per unit time all the time, and D is pure stretching. So, pure stretching means, in a generalized sense, means both change in angle starting from a square, it becomes something like this, and the change in length also, right. So, and together if you combine these two, then you get something like this, right. So, this is just a pictorial representation of what is happening. So, nothing very serious. Now, let us talk of the objectivity or frame indifference. Now, as I said, in the spatial configuration, not in the referential, in the spatial configuration, because we are now talking of spatial vectors, spatial tensors. L is a spatial tensor. Consider two observers or change of coordinates, simple change of coordinates, right. So, x star is qt, which is a orthogonal matrix, times xt plus ct. Ct is a translation, qt is a rigid body rotation. Such a change of coordinate should not create new physical phenomena, it should depict the same physics, right. So, it should not change the physical predictions. Now, let us understand how a spatial vector h small xt is called objective or frame indifferent if under the change of coordinates here h star, that is the h, the original vector represented now in the new coordinates, that is h star, that if it transforms like q times h, qt times h, then it is called objective. Similarly, a matrix is called objective if the matrix or a two tensor A is called objective under this transformation of coordinates if A star is equal to q A q transpose, where A is the representation of the tensor in the x coordinate and A star in the x star coordinate, you understand. So, A star is a function of x star and A is a function of x, all right. So, in order to see this, you can easily see this, because a matrix essentially changes a vector, right. So, you can think of H equal to some A times G, right. A is a tensor, all right, and then you basically now write H star is equal to QH, right. H star is QH, but H is equal to AG, right, QAG. Now, G star I can write as again QG, because G is also a vector. So, I can write G star as QG. So, then Q is proper orthogonal. So, Q inverse is Q inverse is Q transpose. So, basically G I can write as G star Q transpose. So, basically Q transpose G star. So, therefore, I can write this QA instead of G, I will write G in terms of G star Q transpose G. Now, this has to be A star, right, because this is the relationship, sorry, this is G star. So, therefore, this has to be has to be A star, because this is the relationship between H star and G star, right. So, because the original relationship was between H and G through A, this is A star. So, A star is Q A Q transpose, you understood, right. Okay. So, we have the following such transformations under the change of spatial coordinates. F star deforms changes as Q times F. So, therefore, it does not change like a tensor. So, F is not a proper tensor, it is not objective at least. You can call it a two-legged tensor, but it is not objective. Even for material tensors you can apply this, like C is a purely material tensor. So, since the material configuration is not undergoing any coordinate change, so therefore, C star will remain as C. You can easily see that, because C star is F transpose QF, which is F transpose F itself. So, that is why we say that C is frame invariant, not indifferent, but invariant. It does not get affected at all, right. We also say that this C is objective in such cases. So, objectivity is a general notion which is applied to both frame in different tensors in the spatial configuration and frame invariant tensors in the material configuration, right, and so on. So, let us move on now. We need not continue talking about the same concept now, right. Let us talk about small strain now. Small strain is something that is very useful for a class of problems. You have been introduced in your earlier classes to solid mechanics through small strain, right. In the context of continuum mechanics, the small strain, so in the small deformation case, when small strains are involved, there are no two multiple configurations, there are no two configurations, only one. It is the referential configuration only on which everything happens. There is no deformed configuration. So, therefore, in such a case, F is a transformation from the material to the material configuration. You understand? There is no deformed configuration now. And you can think of displacement as a function defined on the original configuration. That is the, you call it by undeformed configuration or referential configuration, because there is no other configuration. So, just call it body configuration, right. So, U is a function on that body configuration. So, F is also a transformation from a vector taken from the body configuration, from a tangent space on the body configuration to a tangent space on the same body configuration, and F is written as I plus identity tensor on the same configuration and grad x of the vector U, which is basically the displacement vector, right. So, in such a case I can define the strain to be equal to half of the symmetric part of the gradient of U by requiring the nonlinear terms in F transpose F to go. So, if you expand F transposes F using this expression for F and remove the nonlinear term which is grad U transpose grad U, then you get basically this expression for the small strain. The problem with small strain, especially in large deformation scenarios, is that under change of coordinates, this is, let us say, a change of coordinates. Let us consider another coordinate q xt equal to qt times x. You will see that there will be some strain, which should not be the case. Under a rigid body change of coordinates, there should not be any straining, right. But you just put this back into the expression for grad u, you will see that grad u is nothing but q minus I. So, epsilon becomes not equal to 0, which is not appropriate. So, small strains have their problems in terms of loss of objectivity, so you should be careful about this. We also talk of the Henke or logarithmic strain, which is a very important aspect of strain and a definition of strain. This is another strain that we often use in plasticity. So, basically from polar decomposition we know that F equal to Ru, U is the right stretch, and the Henke strain is nothing but log of U, right. The advantage of this is that under incremental analysis of the overall displaced deformation, what actually happens is these Henke strains get added. I will explain this in a later lecture properly. It gets just incrementally added, right. So, that is a great advantage. So, this is therefore very useful in finite strain plasticity, where a very large strain is decomposed into smaller strains and then the analysis is done over small strain increments. Okay. Now, let us also talk about why we use multiple strain measures. So, Green-Lagrange strain E, this is E, right, that is purely reference based. Now, we also can talk of another strain, call it by B, which is basically F transposed. You can easily see that this is a purely spatial representation of strain. This is called the Almancy strain. Okay. This is purely spatial, right. We do not bother much about B because we are essentially interested in transferring everything to the referential frame. The Henke strain we have already talked of. This is a logarithmic measure, very good for additive decomposition of the applied force, right, and the additive decomposition of strain in the solution. So, the choice depends entirely on the modeling requirements. Okay. So, but small strain nevertheless remains useful. So, we will use small strain to begin with in the introduction to plasticity. When we come to that stage, we will actually use small strain, because you know, if you use large strain, the problem is that I have to define multiple configurations. And then the discussion becomes very much cluttered. But if I use small strain, there is just one configuration, the body configuration, nothing else. So then the understanding of plasticity can be much better, because I don't get distracted by the multiplicity of the placements of these coordinates, right? Placements of the body, original material body, in the referential as well as deformed. So therefore it affords an easier understanding of the basic plasticity model, right? And in practical applications, many applications require small deformation. So in such cases, small strains are useful, right? It is computationally useful. So that is why actually we will continue to use small strain for some time, and we will come back to the large strain plasticity later on. Yeah. So let us talk of the summary of this lecture, you know. So basically what we have done is we have talked of the effect of deformation gradient, the local effect always of deformation gradient as a tangent space object on infinitesimal line, infinitesimal area, and infinitesimal volume transformations, right? How these actually transform, these things transform under F. We have also understood the polar decomposition of the deformation gradient, which separates stretch in a generalized sense from rigid rotation, right? And the strain is defined in such a way then to ensure that this rotation part in this polar decomposition does not come and affect that strain measure, right? And then we have discussed about a few strain, not all, just a few strain measures to be used depending on the problem at hand, right? That also includes the small strains that we have discussed, even though it is not objective. But objectivity is fundamental, especially if you are discussing large deformation, because the rotation effects can be very considerable, and the objectivity therefore will come into play there, you know, because a change of reference frame, if you do, and if your strains are not objective, then you will be getting a different answer, completely different answer, which you won't get if you use small deformation, because that will be a slightly higher ordered thing that won't come. So these tools form the backbone of continuum plasticity. We have so far talked only about the kinematics. We will be continuing with some basic aspects of continuum mechanics of solids first before getting into plasticity, because these are all tools that we make use of whilst discussing continuum plasticity. So thank you very much for your attention, and this concludes the part 2 of lecture 2. Thank you again.